Hello, and in this video I'm hoping to make the theory I mentioned in the previous two videos come together and explain how a useful amplifier can be made and show one working. So the first equation we derived were the bias equations, this one here and this one here, for the plate current and the plate voltage. So in effect, what we have here is you would set V grid and you would choose a value of R based on signal input and impedance considerations, and then from that point what you would do, and this would be fixed probably, the supply voltage, you would choose a 2 with a desired mu in R plate, and you would set your desired bias current by fiddling with these factors, and then you would plug this from this equation into this equation right here. And in so doing, you would set the plate voltage and the plate current and the grid voltage, and you would have your bias scheme. And then you can manipulate this equation here, where R is this resistance and R plate is inherent to the tube. R plate and mu are the two factors. And then you would find your voltage gain, which when R is large is approximately mu, because these cancel to give unity. Okay, we've derived these, and so the listener can understand where they came from. So let's take a typical circuit. All right, R is 35,000 ohms, mu is 20, RP is 7.7 K, and the supply high potential is 165 volts. When we work the math here, so we have the above equation, 165 is the supply, 20 is mu, minus 2 is the grid voltage, 7.7 K is RP, and this is big R, which was chosen, which gives us a quiescent current of 2.9 milliamps, and then we can feed this back down into this equation here, as mentioned, which gives us 165 volts minus 2.9 milliamps times 35,000 ohms, and that gives us 63 volts. This is significant because you want to give it room for voltage swing. It's called midpoint bias. So the ideal bias would be 165 divided by 2, which would be around 80. But we got it to 63. That's pretty good, because what you want is to be able to give this vacuum tube the ability to swing alternating currents in either direction. The ideal bias at VP, and this is VP, and IP conventionally is flowing this way. The ideal bias condition, midpoint bias, would be V supply divided by 2 would equal V plate, as indicated. That's called midpoint bias for a Class A amplifier, which this one is. Then we work the math, and as you can tell, big R is 35K is dominant. It's 35 over 42K. You can roughly cancel that out, and the voltage gain is roughly mu, or 20. All of this was derived in the previous video, and so now we have our circuit. We chose 35K based on bias and gain concerns. And you can fiddle with these formulas and choose values that give the right bias or the right gain or both. Or you can change the tube if you need a different parameter of RP and mu. And then we biased the grid with a minus 2. And this was done without a battery, using something called self-bias. So let's start this off relatively simply. You put a 1 mega ohm resistor between grid and ground. It's called the grid leak, and it's because occasionally as electrons move across this guy, some of them collide with the grid, and when they do so, they can sometimes stick on the grid. So if the grid was left unconnected to anything, it would turn the tube off because the negative electrons would get stuck on it and repel other electrons from going past it. That's enough theory for the moment. So we do the following. We put 1 meg resistor between there and ground. You might wonder about what this resistance does. Let's call it RC. That's our self-bias resistance. In the previous example, I used a battery to bias this thing. In this example, we're not going to use a battery to bias it. We're going to actually instead make it bias itself. And how this is done is RC is set to the value of V grid divided by I plate via Ohm's law. So what we have is effective conventionally, we have 3 milliamps here, roughly, and we need 2 volts. And when you work the math, you would have 2 volts minus divided by 2.9, and then that would give you your 770 ohms, which is what's used there. And then what happens is the cathode is above ground by 2 volts. This is the cathode here. And the grid, because it doesn't draw any current, is at ground, so it acts as if there were that imaginary 2-volt battery. But nobody wants to go around having to replace amplifier batteries constantly. So this is why it was done this way. Now, of course, you would put a coupling capacitor here, making a high pass network, and then your input voltage would go here, as so, just like this, Vn. And then your output will be taken across the plate. And again, this is your cathode K, your grid G, and your plate P for this triode, 6J5, and your output voltage would be between here and ground. But in practice, it could be capacitively coupled to another amplifier stage, as shown here, and this could be another 6J5. Alright, so we designed our common cathode amplifier. It has a very large input impedance of 1 mega ohm because the grid doesn't draw any. It has a grid voltage of negative 2 volts set by self-bias. This guy is only 770 ohms. This guy is thousands, so it doesn't really interfere. Okay, then we have a current flowing of 2.9 milliamps and a bias potential at the plate of 63 volts. And so we have a bias point, and we have a voltage gain of around mu based on this equation here, 20 volts per volt. And what we can now do is we can find a way to cascade these stages. And when you cascade amplifier stages, so if your actual input signal is here and then you run it past another amplifier here, which would have its own resistor here, and probably have self-bias as well going on, then you could drive another stage, and every time you keep cascading these things, the voltage gain is the product of all the gains of all the stages, assuming you have the impedance matched. So basically I've showed you how to bias, how to find voltage gain, and how to find input and output impedances. Now the input impedance is dominated by the grid leak, which is 1 mega ohm, the lowest resistance there. It's still very large. And your output impedance is dominated by the 35 kilo ohm. Now, if you want to do it technically, it's 35K in parallel with RP, but RP is little, and in practice, this guy has a much larger effect because he's what's limiting your swing, the plus rail. And effect though, so now we know how to bias it to get it going without us. You have to have your steady state DC signals, how to figure the gain, and have some idea of the input and the output impedance dominant factors. And then in the next video, I'll show you the amplifier I made, and then I will show it work, amplifying direct currents, and this will complete the lecture on vacuum tube theory. Shortly hereafter, I will give a lecture on transistor theory. And if you watch this series, then you are one step towards understanding transistors. They're very similar. Only difference really is that vacuum tubes use mu and RP. Transistors use something called beta. Another quantity of interest would be VBE, which is well known. And in FETs, they have GM. But basically, the equations are very similar to this. So I hope everyone learned something, and that's it for your basic vacuum tube voltage amplifier common cathode theory. And this is the most common amplifier when you look at old radios and televisions and guitar amps. And basically, this is vacuum tube theory part 1. And so in this video, I'm going to document system level amplifiers. So effectively, you have three main parameters: your input impedance, your output impedance, and your voltage gain. Of course, there are others, although they are related to these. Your input impedance is how low a resistance your input sees, and for tube amps it's really high, it's 1 mega ohm, and you can use higher. You want this guy, your input impedance, ideally he would be infinite. Your output impedance is a different matter. It's on the output, which is the plate. This is your cathode. This is your grid. So your output impedance, the largest impedance it faces, is R, which is what it was called in the last video. And here it is 35 kilo ohms. Ideally, this guy would be 0. But, worst case scenario, you have to keep your input impedance much larger than your output impedance. And as you can see, this guy is orders of magnitude higher, so we're good. In other words, what you can do is you have your 35 k ohm output impedance, and you're trying to hook up that to another amplifier, and that would give you 1 meg. In other words, by the voltage division rule, most of the voltage applied between here and here, which we can call Vn, most of it will show up across the 1 meg, which is what we want. Actually, the ratio that appears here would be 1 meg divided by 1 meg plus 35k. And as you can tell, times whatever Vn is, and that is what would appear between here and there. So now you can see why you want a low input impedance. Let's go ahead and erase this. Alright, so in practice, what you do with amplifiers is you can't really get a larger gain than so much. So what you do in practice is you cascade them. So in the amplifier I made, you have your first amplifier, we'll call it A, which is this circuit here. And then that one goes to another amplifier, also called A, and then this one goes to another amplifier. And each of these has a gain of 20 volts per volt. 20 volts per volt, 20 volts per volt, and the output appears here. Well, the gain is minus, so technically minus, 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 plus, plus, minus. So the whole total gain is the product of these, which is minus 8,000 volts. So you can see how, although the gain of any one stage is not very large, if you keep cascading them, you can get gains in the millions and billions. In fact, you can get gains so large that all you hear is noise, little disturbances that don't matter. Not this case, however. Okay, so I took this amplifier and reproduced it 3 times. Each one is one copy of this circuit. I explained how the voltage reaches the input because of the high input impedance and the low output impedance. So this behaves like a 35,000, like a 1 meg resistor. This is your N. And your final output has a resistance of 35k, which is good. It's the criteria we want. You want a high input and a low output resistance. Impedance, Z. Same thing. Impedance is the more general resistance. Okay, now here's my magnum opus, my point of these videos. What you can do is you can make this amplify direct currents, and here's how it's done. Okay, remember this circuit I'm going to erase. It's done like this. Okay, erase. So, how this is done, you have your amplifier. Same circuit I just showed. A. Of course, these are actually filter caps, but they act as short signal frequencies. Your final cap, your input. These were all 1 microfarad. So your total gain here is 8,000 volts per volt per the math earlier. But you might wonder how it's possible to get direct current amplification when these only pass AC. Well, the answer is really simple. You just have a relay here, and this would be ground, and this would be your input DC. Probably have a capacitor here to filter him, so only the DC gets through. DC, yeah. And this guy has a coil running him, and over on the other side, we have the same thing. You would have another relay in sync, and again this would be ground, same ground, and then this guy would have a capacitor to rectify. And of course the coil on this relay would also be run from the same, and we can say that this goes to 25 hertz square wave. So, and this would be your output. So one way to amplify DC as an op amp would do, and this entire circuit actually behaves like an op amp. This entire circuit behaves like an op amp, where you have the positive lead at ground and your negative is your input. And this would probably behave something like a UA 741. Okay, so now you might wonder, well, it has a gain of 8,000 volts per volt. So if you put any little signal here, and it would be negative, or you might use positive. Say you have a -3 volts. That's going to try to give -24,000. You can't do that. Well, we can use negative feedback. And what you would do is you would hook up your feedback resistor from output of the DC side to input. There's your feedback resistor. And your traditional input resistance would go here. And in that case, what we would have is an inverting amplifier, R in it here, R feedback. And of course, everyone studies this circuit in circuits 1, circuits 2, or the like. So you know your output here. And I'm sorry about the glare on this board. You can't see this when it's here. Your output here would be minus RF over RI times VN, where of course VN is between there and ground. So we've effectively made an op amp using vacuum tubes, which is what I wanted to show, how you could do this if you were stuck in the past and you had an op amp below in your time machine. Well, you can get around it. See Back to the Future. Forget whether it was 2 or 3. They used tubes to replace an IC. That's basically what we're doing here, just to show how it could be done. Okay, so we want an amplifier with a gain of 5, not 8,000. So we can set this guy equal to 500 kilo ohms right here, and this guy would be 100 kilo ohms. So it matches the impedance well. The 1 meg that this tube has is large in comparison to that, and that's our goal. So most of the signal gets there, and then this 500K is very large compared with the 35 kilo ohm output of this amplifier. So the general rule is if you have gain 1, gain 2, and gain 3 voltage gains, the gain of the system would be the product of all the gains from I equals 0 to n, or G1, G2, G3 here. Alright, so this is our DC amplifier. So this could be a thermometer, which would have a range of 0 to 1 volt, and then out here get very reliably 0 to 5, or so on. And you can fiddle with these values to get exact gain. 1, and of course, you flip it around because it negates it. The gain is negative 500k divided by 100k, which would equal negative 5 volts per volt. And this uses feedback techniques. I'm going to have to describe this in a different video, exactly how feedback works. But basically, if you have a very large gain on this amplifier, you can use a feedback resistance that lowers the gain predictably. I've written about this in my senior thesis. But anyways, this is how op amp can be made from tubes. Or for that matter, you could also probably get away with using field effect transistor. For some reason, BJTs do not work well to build op amps, namely because they have a low input impedance, which is bad, and they have a very high output impedance. I mean, the collector of those things is really a high impedance, and you can use emitter followers, but they lose voltage, the VBE drop. Maybe you could use a BJT if you were clever. But the tubes work really well, and I will now show this instrument in operation. Look, what I meant to say is you have this relay here, and then you have the output relay there that chatter in synchrony. So this guy actually converts the DC in to an AC signal with its peak amplitude equal to this DC in. And then this goes through the AC amplifiers and gets rectified back into DC in a way that you can use negative feedback in this large capacitor, which is 100 microfarads, or a millifarad you could use in reality, very large. So that's how you can amplify DC. This is the big picture. You take it, convert it to AC, amplify the AC, convert the AC back into DC. You could use transistor switches, thyratrons, or diodes if you wanted to, but this is the big picture. If you can't do it one way, you can convert it from one to the other, do what you need, then convert it back. And I think this is a very nice example for how a classroom of students could build their own operational amplifiers in a day. No differential stage needed. In practice, this plus node mostly goes to ground, so actually this guy can do anything a regular op amp can do. You can just use negating ones and then adding to make a differential amp or an instrumentation amp. But I wanted to make this point clear. And here it is, my magnum opus. You have a 3-stage vacuum tube amplifier right here, and it uses my favorite 6J5 triode. If you need a triode that'll do general amplification and is reliable, there's nothing quite to beat the 6J5. Do not touch any pins. As you can see, I use 1930s brass screw construction. That provides the filament. Literally the wall power comes directly from the wall after a half-wave rectifier. And this is the relays that convert direct into alternating, amplify the alternating, and then convert it back to direct. And your feedback resistors are those two. The filter cap there is what's on the rectifier side, and these are just for stability. This function generator here is what's timing the relay. So the gain is 5. So for instance, if we turn this one, which is your input voltmeter, all the way down to a -1, takes a second to get it there, 99, it's really close. We can see on the analog -1 scale here, 12 volt scale from the knob, it's almost exactly at 5, which would be that tick right there. We can do other values. For instance, -0.5 volt. Alright. That's pretty close. Would give us 2.25, or 2.5 ideally, and it's pretty close, 2 and then some, almost exactly 2.5. That one there's 3 on the 12 scale. Okay, we can also do larger values. 0 zeros it, as you can see, a little bit of back bias, and let's increase this thing. Let's go all the way up to, well, 3 volts would be off the scale. Let's do 2. And you can get really precise with it. That's pretty close.
2 volts times 5 would give you 10 volts, which you can see right there is what it gives. It works. It amplifies direct currents. One final one would be 1.5. What would that give us? 1.5 would give us around 7, I think. 7.5. And as you can see, 7 is right here, and it's just 6 and 8 just over it. It's not entirely accurate. I've used 5% components or 10%, but it works. It amplifies direct currents. Now, as you see, when you change the input up or down, there's actually a delay caused by the rectifier cap trying to discharge to the right value. Well, 0.2 would give us 1 volt, wouldn't it? 0.19. And you can see we wait and it moves, and when it stops moving is when it's equilibrated. Okay, this is 0.25, which would give us 1.25. 0.25, 0.2, close enough. It's almost 1 volt, 0.8 or something. And it's not quite accurate, but it works. Amplifies direct currents. And so it goes from DC to AC, amplify the AC, rectify the AC, back to DC with the feedback, and there you go. So I think this is a pretty interesting circuit. When you turn it to 0, it goes to 0. Let's see one more value. Let's say we had 3. Let's see if it'll give us 15. I think it will. My money's on it giving 15. Oh, well, it only goes up to minus 2.24. And that's off the scale. Our battery is weak. Ah, shucks. Let's just try let's just do 0.75 and see what that gives us. That's pretty close, 0.74. And that would give us, we get 0.75 is 3/4. Give us 15 quarters, which would be just under 4 by 0.25. So it would give us 3.75, and this one gives us 3.5, roughly. Well, as you can see, my supply battery's dying, so it's not completely accurate. But this is it. This is the vacuum tube amplifier, and as you can see, it gets capacitively coupled in. That's the grid. Ground is the bottom one. The filaments, these two. Cathodes, the next one. You can see it goes from plate, capacitor, next grid. That's your grid leak right there. 770 ohm or 35 kilo ohm. We're close. Cap out, cap in. Self-bias resistor network is here. And these guys get awfully hot, awfully fast. This one here is just roasting. I used a lower resistor to get him the right impedance. Anyways, that's it. An op-amp made entirely from vacuum tubes, and it works. Approximately. But I imagine if you could use more precision parts and tubes that weren't 60, 70 years old, it could do a lot better. But this is the proof of concept.